4.2 day 2 experiments. We're going to continue with this idea about the coffee experiment because it's a really good way to outline what a good experiment entails. Step 1 from the previous notes was we need to have a control group. So we give students in the class coffee, and then we give another group in the class nothing. And then we compare like the average pulse rates between the two groups. So we need to have a control group for comparison. The second thing we need for good experiments is we need to make sure we need to do everything in our power to make sure that everything is kept exactly the same between the two groups. The group that didn't get the caffeine and the group that did get the caffeine. We need to keep as much as we can exactly the same between the two groups. Like the amount of caffeine, for example, or how long we wait until we monitor their pulse rate. Everything needs to be kept the exact same, except for obviously one group gets caffeine and the other group doesn't. And then to go along with that, we need to make sure we randomly assign people to which group is which. And in doing so, hopefully that balances out the kinds of people among the treatment. Because I can't do anything about certain kids that have a higher caffeine tolerance or lower caffeine tolerance or faster heart rates in general or how much coffee they drank before class. So some of that I cannot control. So if I randomly assign the kids to which group they're in, we're going to trust that random assignment will hopefully balance out those other factors in general. So that's the other key here, is random assignment. We know we need a control group. We need to keep everything between the two groups exactly the same, except for the treatment. And then we need to make sure we randomly assign the students to which group is which. So whether it's the caffeine group or the group that gets no caffeine, just to balance out maybe the type of kid that goes in each one. We're going to trust the random assignment. So how do we randomize? And you actually should know the answer to this question. How do we randomize? How do we randomly assign students to groups? Because we've learned 3 ways so far. In those 3 ways, you can either use the hat method, that's probably the easiest one, the random number generator using technology, or the table of random digits. Hat method, probably the easiest one, and the easiest one to explain when you got to write it out. There's not much you can mess up. I mean, identical slips of paper, mix it up, and draw it out. Okay, and then in general, what's a completely randomized design? For an experiment, this is another vocab term. A completely randomized design. You take the subjects or the experimental units, and they're just assigned to treatments completely by chance. So you literally just randomly assign it. That is a completely randomized design for an experiment. There'll be a couple other types of experiment designs we'll look at, but a completely randomized design just takes experimental units or subjects and just assigns them to treatments at random. Okay, so what's 2B here, the other key component in designing an experiment? That is replication. And replication means ensuring that there are an adequate number of observations in each treatment group, so enough people, so that the two groups are as equivalent as possible. Then the differences in the effect of the treatments can be distinguished from chance differences. So this kind of has to do, it's kind of related to sample size, even though sample size refers to observational studies. Replication means you can repeat your experiment enough times on enough people that we can actually start to see the results take effect for like the whole group. And then once we see the results take effect for the whole group, that's when we can rule out the chance differences. So it's important for us to be able to replicate the experiment enough. If we can only do it 3 times on 3 individuals, then our results aren't that trustworthy. And the other thing that replication does, if it's a good enough experiment, then somebody else can perform your experiment somewhere else. And if that applies, if it's a good enough experiment to be able to conduct somewhere else on other people or similar subjects, then that helps us extend our results to a larger population. So if we have a quality experiment, we could replicate it on a lot of individuals. Then that helps us say, like, Well, that helps us say something about the greater population. That's our inference. So if our experiment design is good enough that we could replicate it to the point where we could do the entire thing again with different subjects, that builds our confidence and makes us think that our results are good enough to extend to the larger population. So replication, another important component for experiments. 2C, that's control. And I'm not just talking about control group. I'm talking about having control of everything that goes into the experiment and watching it closely. So that means holding all the other variables constant for people in both treatment groups. And that will prevent confounding. For example, if one of the groups puts sugar in their coffee, or like this describes if you have a group that drank sugar-free Coke, like Diet Coke, and then actual original Coke, which has sugar in it, then you wouldn't know whether their pulse rate was increased by the sugar or whether it was actually increased by the caffeine, because you have more than one variable there. So the idea of control means you need to control and keep everything the same as best you can. You need to keep everything the same for both groups except for the treatment. And then you can actually observe whether that treatment had an effect or not. And then the other thing that control does is it reduces variability. And the easiest example of that is if we're drinking coffee or soda for the caffeine experiment, is that we have control of how much each person gets, and we need to control that to be exactly the same. Which obviously means then we couldn't trust the results. Everyone needs to get the exact same amount so that we can compare the amount of caffeine or soda or coffee that you drank won't be one of the other variables we have to take into account. And these two dot plots, just examples of two caffeine experiments. And one of them, it actually featured control. Like each student drank the same amount of caffeine here in the caffeine group. And obviously the no caffeine group didn't get any caffeine. In the second one, the caffeine group, they were allowed to drink as much or as little as they wanted. And you see how much variability that created. So if you're the person running this experiment, you'd be much happier to see something like this. Like, oh wow, look at the caffeine pulse rates. They're much higher than the no caffeine pulse rates. Whereas this, yeah, I guess they look higher in general, but there really is a lot of overlap. So it's hard to prove that caffeine, in all cases, would raise the pulse rate. This is a much stronger argument here. Obviously, caffeine raises pulse rates, but this one up here, almost the whole group was above the no caffeine group. Okay, component piece at the bottom here. It's also important that all subjects in both groups are blinded. I'm not talking about physically blinded. I'm talking about experimental vocabulary blinded, which means that they don't know what treatment they received. Otherwise, they might be subject to the placebo effect. Let me give you an example of this. Let's say we serve coffee instead of soda. Then I would randomly assign students to the two groups, caffeine, no caffeine. But I would just give one group caffeinated coffee and the other decaffeinated coffee, and they wouldn't know which one they got. Otherwise, my results could suffer from the placebo effect, and that's a very real thing. If you think you got a treatment, then somehow your body starts responding, your mind starts doing things in accordance with like what you would have done with that treatment. And if the people in the study and the people who are observing the study don't know who got what treatment, that's called double blind. So the people who are like writing down the results from each individual, if they don't know who got what treatment, that's called double blind. And they do that so there isn't any bias created by the people writing down the results in case they have any predispositions or beliefs about the study. Scrolling down here, if a study is blind, that means the people in the study, they don't know what treatment they got. If it's double blind, that means neither the people who got the treatment who are in the study, nor the people who are recording the results, who are like running the study, know who got what treatment. How does that work? Well, there will be one guy at the top, like a statistician, for example, who knows exactly the people who got the treatment and who didn't. But the people actually working for him and conducting the study, they may not know, and that's a double-blind study. And then one quick note here. It's not like every single experiment ever done has to have a control group or a placebo. For example, if you're testing a new drug, it's usually compared to the current drug and not just a placebo. It's like, although some drugs do try to do that, just say it's better than taking nothing. Congratulations. But in general, it's better if they just compare it against the current drug. They don't need to just give a placebo. Also, you can do an experiment to compare 4 brands of paint. Right? You can compare 4 brands of paint in an experiment, and you don't need a placebo or a group that didn't receive anything. So it's not like you have to have those in every single type of experiment. Okay, so in summary, 3 major components we saw. The first one is random assignment. That hopefully balances out all the factors like different type of people. If we can randomly assign them to treatment groups, then we can trust our results. Second one was control. So we make sure everybody in both groups gets the exact same thing, and we monitor it very closely. So the only thing that we're changing is actually the treatment. And the third one is replication, which means if our experiment's good, we can perform it on a lot of individuals, a lot of subjects, and somebody can take our results or our directions, our study, and do it on a different group of people somewhere else. So that means they could replicate our experiment. First example here, television and young children. Psychologists want to know how different types of television shows impact young children. They recruit 64-year-olds, I'm sure that's difficult to recruit, and have them watch 9 minutes of a fast-paced children's program, defined as scene changes every 10 to 15 seconds, watch 9 minutes of a slow-paced children's program, defined as scene changes every 30 to 45 seconds, or draw for 9 minutes. After the 9 minutes, each child will complete several tasks, including tests for mental ability, and impulse control. Just fix that word right there. Mental ability and impulse control is what they're going to monitor. So describe a completely randomized design for this experiment. Write a few sentences describing how you would implement your design. Okay, so looks like 3 treatments here. Either they're in the fast-paced television group, they're in the slow-paced television group, or they're going to draw. So there's 3 treatments. We've got 60 kids, so let's assign 20 to each one, right? So let's be really clear here. For the AP exam, you need to be able to explain this, so I could give it to another AP Stats student, let's say, and they could go actually conduct this experiment. So let's be really explicit here. So the first thing is we need to randomly assign these kids to which treatment they get. So that would be easiest with a hat method. So let's start with 60 identical slips of paper. Make sure they're exactly equally sized, of course. And then I suppose we could put each kid's name on it and then draw them out that way. In this case, one way we could do it is label each type of paper, like label each one with a 1. So put 20 slips with a 1, 20 slips with a 2, and 20 slips with a 3. And then just have each kid come up and draw out of the hat, and that'll decide what group that kid is in. So that's another really easy way to do the hat method, that we don't have to like label all the kids' names and so forth. Like if they're all just standing there, we can put the 1s and 2s and 3s in a hat and then have them just draw from the hat, and then I'll tell them what group they're in. So mix the numbers well, and then have each child draw. Have each child draw a number without looking. Don't let them cheat. And so that'll basically tell us what group they're in. So the number chosen by the child will be the assigned group. Okay, so I think that's straightforward enough that someone could definitely go and conduct that and not have any questions for me about clarification, right? If there are no repeated numbers to worry about or anything like that, you just have each kid draw, and that's the group they're in. So that's pretty clear. Okay, so once we get all the kids in the group, conduct the experiment, right? And then at the end, this is important, at the end, what are we going to monitor? What do we care about? So what do we compare? At the end of the study, tell me what I should look at. Tell me what the results are going to show or what I should see. So I got kids in the fast-paced group, the slow-paced group, and the read a book group, or draw a picture group, actually, that's what it was. So at the end, we need to observe the mental ability and impulse control between the three groups and see how they did on average. So I need to make this note here. So like if I'm telling someone how, like, okay, I know how to do it. I know how to get kids in groups, and I know what they're supposed to do in each group. But then at the end, what am I supposed to look for? So you're going to compare the mental ability and impulse control for the three groups. That's the whole point of the study, and this is like our conclusion. We need to tell the people who would be conducting this experiment what to observe and what to consider when they get done. All right, last example for these notes. Example 2. It says, in an interesting experiment, researchers examined the effect of ultrasound on birth weight. Pregnant women participating in the study were randomly assigned to one of two groups. The first group of women received an ultrasound. The second group did not. When the subjects' babies were born, their birth weights were recorded. The women who received ultrasounds had heavier babies. So does this prove that getting an ultrasound gives you a heavier baby? Well, there's a couple issues with that, and look at part A. It says, did the experiment design take the placebo effect into account? And why is this important? So the placebo effect means people know they got a treatment, so they're going to just all of a sudden start acting differently. So they definitely didn't take that into effect because the women knew they were in this experiment, and the ones who got an ultrasound obviously knew they got an ultrasound, and the ones who didn't, they knew they didn't. So what will that do? What will the placebo effect do? Like knowing you received the ultrasound treatment, how will that change those mothers? So first of all, no, they didn't take the placebo effect into account, which is actually why we can't trust these results and say like ultrasounds will make your babies heavier or whatever. And the point being this, so it's important because women, the ones who knew they were getting an ultrasound, they were subject to the placebo effect. So if they knew they were getting an ultrasound, well, they would have possibly had different reactions. What would those different reactions include? I don't know. They might have made healthier choices in general because like they felt an emotional connection to the ultrasound, like the screen they saw, like the baby up on the screen. The fact that they received an ultrasound, like they knew they were in the study, so they started just eating healthier and eating more. So it could have just affected them in multiple ways. So that's really why we couldn't actually trust these results. So they could have made different reactions. They could have had different reactions than those who knew they didn't get an ultrasound. They weren't subject to the treatment, so they might have acted differently. So if they start acting differently, that means our results are no good anymore. Part B, was the experiment double-blind? Why is this important? Well, you already know it wasn't double-blind. I mean, the subjects who were in the experiment knew what treatment they got. So the only way like it could have even been partly blind is if the people who recorded the baby's weights, I mean, maybe they did. Maybe the people at the end of the study who recorded the baby's weights didn't know who got what treatment. So they couldn't like try to cheat or make things up or whatever they want to do. So they might have been blind, but it definitely wasn't double-blind. So the people weighing the babies at birth, those people who actually involved in conducting this experiment, they might have been blinded. They might have not known who got the ultrasound, who didn't. But The reason it's not double-blind is because the mothers, they weren't blinded. They knew whether they had an ultrasound or not. So why is that important? Well, the mothers, they may have affected the results, right? They may have acted differently based on the placebo effect because they knew what group they were in. They knew if they got a treatment or not. Okay, so could we propose a better design for this one? Ethically, of course. That would take into account the placebo effect. Like the moms, like, they knew they got an ultrasound, they're watching the baby on the screen, they have this emotional connection to it, and then versus the moms who weren't in the treatment group, and they knew they weren't in the treatment group. What can we do to account for that? So one thing we could do is actually go through the process of giving everyone an ultrasound, and then just don't show the screen to the mothers. So if we just treat all mothers as if they were actually getting an ultrasound. So actually use the ultrasound machine, put on their belly, so forth, but then we don't show them the screen. And obviously, like I said, it has to be ethical, so they would have to know that they're participating in this study. Otherwise, that's not going to be ethical. So for some mothers, the machine would be off, so they actually wouldn't be getting an ultrasound. And then for other mothers, the machine would actually be on. So this must be done in such a way, though, that the mothers couldn't actually see the screen. Because if they saw the screen, then obviously they would know that they were getting an ultrasound. So one way to make sure the mothers don't know what group they're in is to go through the process of giving an ultrasound to every single mom, but make sure they can't see the screen, because some are actually going to get the ultrasound and some would not be getting an ultrasound. Okay, so the stuff on this page is really just an overview of the principles for experimental design. There's 4 big ones. Comparison, so 2 or more groups compare, whether it's just caffeine and the group that gets nothing, or if it's caffeine and sugar in the group that gets nothing. You need to be able to have groups compare to. Random assignment means you randomly assign the experimental units to the treatments. Control, keep everything the same as much as you can between both groups. Replication, be able to perform the experiment on multiple subjects and hopefully be able to replicate the experiment for someone else in a different location with different subjects. So those are our 4 components for experimental design: comparison, random assignment, control, and replication. And this guy down here, this is an outline for an experiment. So this is just an outline. And when you're doing this on the AP exam, the outline is not enough. You need to actually describe in complete sentences like we did before, as opposed to just giving this outline. This is really good, though. This is a good diagram. So how does it work? You have these experimental units, the people involved in the experiment. You randomly assign it to 2 groups. This one gets a treatment, this one gets a treatment. Then we're done, we compare the results and conclude whether the treatment had an effect or not. In the last page here, I'll leave the exam tips to you and a fun little comic about placebo. See you in class.